All right, clip number 2 on Chapter 11, Section 6 notes on surface area and volume of a cone. Clip number 1, we explored the two-dimensional measurement being area, surface area of an unraveled three-dimensional cone. This clip, we're going to now get back to volume, a three-dimensional measurement. So we're going to be fundamentally dealing with cubic units. This is the space that fills that cone. To use the ice cream analogy, if I was talking about surface area of a cone, we're talking about the amount of material needed to make that ice cream cone itself, the waffle cone or whatever. And then if we're talking about the volume of a cone, we're talking about the ice cream that fills it up. All right. So the main punchline here to be aware of for the volume of a cone is that the formula is exactly the same as what we dealt with in Section 5 when we dealt with pyramids. Volume of a cone, capital V, is equal to 1/3 the area of the base times the height or the altitude or the depth of that cone. This is the same exact formula that we dealt with in Section 5. The difference here is that the area of the base, because it's a cone, is definitely going to be a circle, meaning that capital B is just going to be pi r squared. Quick side note here, as far as the fact that we have to have this r, this radius. In a lot of problems, they're going to present that to you in several different ways. I've mentioned this in several other recordings as well. In a lot of cases, like in the diagram you see down here, or some of the examples that we've already done, they'll just explicitly tell you what the radius is, the distance from the center of the circle to its side. But in other cases, they could totally tell you the diameter of the circle, in which case you would take that value and cut it in half. They could tell you the circumference of a circle, in which case you would take that circumference and divide it by 2 pi. And those are just different ways it can be expressed to you, where you have to do a little pre-step to find out what radius is. So all that stuff is still eligible. That's stuff that was talked about in Chapter 10 with circles and stuff. Okay, and then again, you'll notice, just like in the previous couple of sections, I showed you the perfectly upright cone versus a tilted cone. Again, just like in Section 4 and Section 5, I don't care about how long this side is right here. I'm simply caring about the perpendicular height, the altitude, the depth compared to, if I were to imagine setting this cone on my desk, what is the actual vertical height of that cone, however tilted it may be. Okay, and the example we're going to work through actually shows a tilted cone, so you'll see that at work right there. And I'll talk about the different variations you might see there and how you would calculate out for what you would need. Okay, so again, like many of these formulas for volume, there are basically 3 measurable elements that are going to be plugged into here, whichever one I may be solving for. So capital V, again, represents a volume. In some cases, you may be given that volume. We talked about some of those examples at the end of Section 5. And so if I am given a volume, that's what's going to replace capital V. And if I'm solving for one of the other pieces in that formula, I just have to make sure I do inverse operations to get stuff over here. Something to point out, a lot of students struggle with moving the 1/3. The way I would do the inverse operation of moving the 1/3 to the other side, so say I had to solve for radius or height, the way I'd move the 1/3 to the other side would be by multiplying by 3. Okay. Or maybe I'm given radius and height, like we're going to be seeing in this diagram, in which case I'm doing all my calculations here on the right-hand side and then solving for volume. And in those cases, again, a lot of students get hung up on how to deal with this 1/3. Just as a piece of advice, if you want to write this in your margins, what I would do to deal with this 1/3, because a lot of students get intimidated with fractions, do all this other junk first. Pi, or 3.14 times whatever the radius is squared, times the height. Do all that junk, you're going to get some number. And then when you multiply by 1/3, the simple thing to do on your calculator is actually just divide by 3. Okay? So anytime I multiply something by 1/3, like what's happening here on this side of the equation, that's just the same thing as dividing by 3. So on a calculator, that's how it can just be kind of summed up there. Do all this other junk, pi r squared times h, and then just divide it by 3, and that's the equivalent of multiplying by 1/3. Okay? Just to keep that in the back of your mind. Okay, well, let's apply this to an example. right? The one that you see on the screen here, just breaking down what you'll see in the diagrams, the different variations you might see. Okay, again, in this formula, there are three measurable things I'm going to care about. Am I given volume? Am I given radius? Am I given the height or altitude or depth of the cone? In this case, I'm given the radius and the height of the cone. So this 2.2 centimeters here is going to go in for the lowercase r. This 4.5 centimeters here is going to go in for the h. So I'll be able to solve directly for capital V. In some cases, you'll have to solve for radius. In other cases, you'll have to solve for height. Okay, just plug stuff into the correct place, and you can go from there. So let me jump to the whiteboard to solve this problem. I'll talk about the variations you might see, and then we'll solve it really quickly, and we'll be done. All right, so we're given the following tilted cone. In this cone, some things to be aware of here. Very important feature that might be overlooked by a lot of students is the fact that this is a right angle right here. That's important because the fact that this is perpendicular to the horizontal base means that this is now the height or the lowercase h in that volume formula. That's important. That will not always be the given case. All right. The other pieces that we're given here, we are told that, in fact, the distance from the middle of the circle to its side is 2.2 centimeters. This will end up being the lowercase r, the radius of that circular base. And for the record, this formula that we saw also in section 5, this is the same exact formula. It's just that this base is pi r squared. The r is going to be going into that piece right there. But then the other piece we're told here is that this side, which happens to be the height, is also 4.5 centimeters. So to just show the same techniques that we did in section 4 and section 5, I'm going to replace that capital B with the actual shape of the base that we have. It happens to be a circle, so capital B is also pi r squared. H is still the height, depth, altitude of this thing. So I'm just plugging in values at this point. So capital V volume here is going to be 1/3 times pi r squared. The r here is that 2.2 centimeters. Be careful here of order of operations. I will have to square that radius first before I multiply it by pi, or the 1/3 for that matter. And then the height, altitude, depth here is that 4.5 centimeters. There's the stuff substituted in for the correct variables. Now I just have to do the calculation part. Again, my suggestion here for you, do this chunk first and then divide by 3 in your calculator. That's the easy way to deal with this 1/3. Again, that's where a lot of students tend to get hung up. So I'm going to do all this stuff first in the calculator. Order of operations dictates that I have to do this exponent first. So I'm actually going to do a step first to deal with that exponent. So volume here will equal 1/3 times pi times 2.2 squared. 2.2 times 2.2, or 2.2 squared, is 4.84. So just doing that really quickly. That would be required to do first. If you didn't square or you try to input in your calculator in the wrong order, you'll get a wrong answer. So make sure that you are doing that r squared first. Because now at this point, now I'll multiply just these three together. Multiplication does not order. It does not matter the order in which you multiply these three numbers, as long as you just multiply all three together. So at this point, I'll go ahead and round that pi to 3.14. Multiply by 4.84. That was the 2.2 squared. I'm going to multiply by 4.5. So that long decimal, that's just those three multiplied together. Right? And now I'm going to apply the 1/3. And again, students tend to get hung up on the fact that it's a fraction. Anytime I multiply by 1/3, that's just dividing by 3. So at this point, this number, which is those three multiplied together, I'm just going to take that and divide it by 3. And there's my volume. So volume here to 2 decimal places. 2 decimal places, I'd go 7/9. The 6 is going to force the 9 up. It's actually going to round up to 0.80. Be careful about that kind of stuff. Units here were centimeters, and the fact that it's a volume, it's cubic centimeters. That piece right there will be given to you on big ideas. So you'll just have to solve for the number. There's the volume of this cone. Things to be aware of here. It could have totally have given me this volume measurement to start with, in which case I would have taken that volume, that 22.8 cubic centimeters, and plugged it in for V. And if I had to solve for, say, the radius of the circle, I would move stuff inverse operation-wise to the other side of the equation to solve for that element. The way I would move this 1/3 to the other side would be by multiplying by 3. Dividing by pi is the same thing as just dividing by 3.14. Dividing by either of these elements, it's just dividing by that decimal. If you had to solve for radius, where there was that radius squared, you would first divide by the whatever h value you had, and then you'd have to take the square root to get rid of a squared to figure out what the radius was. So those are just inverse operations if I happen to be given volume from the get-go. Okay, again, I just wanted to kind of go through this process of showing you a variation right here. Because one thing they could have done, this is just a different example entirely. You can throw this in your margin. One thing they could have done here, let me just draw a different tilted cone. If they say this is a right angle, that's important because I'm going to end up with a right triangle fundamentally hidden within this right cone. One thing they could have told me here is that maybe they told me that the radius of this circle was, say, 1.5 inches. And maybe the slant length was 5 inches. Had I been given this, and I needed to say find the volume of this cone, this slant length does not help me with volume. I need to know the vertical height. I need to know this unknown, let me use a different color. I need to know the unknown h value, which would have to be perpendicular to the base. And so one thing to kind of show here is that there is a right triangle hidden within this right cone, where this would be the h value I'm going to end up needing. This was the 5 units. Something to point out here, if I know the radius is 1.5 units here, this entire length down here would be what we call the diameter of the circle, which is double that amount. 1.5 times 2 is 3. Okay, that's just a different way they could present it. In which case now if I want to solve for this height, this altitude, this depth of the cone, I'm going to apply Pythagorean theorem because it's a right triangle. So in this case, I would simply say like, all right, well, 3 squared plus that h squared is going to have to equal the hypotenuse, side opposite the 90-degree angle, squared. And so in this case, just quickly showing the work for this in your margin, I'd get 9 plus h squared equals 25. Subtract the 9. H squared here equals 16, in which case the height or altitude of this triangle would be 4. So doing that Pythagorean theorem to solve for that height value, again, if I had to solve for the volume of this given cone, I'd have the radius. The 1.5 there would still be the lowercase r in the volume formula, but I would have to first solve for that altitude, that height of the cone, and that would be how I'd work through it. Now I could plug that into the h value in that same volume formula. So that's just a variation of what you might see. It's essentially the same kind of variables. This is just one where I had to do some pre-steps to solve for something I needed. Okay, but that will conclude our section 6 notes on surface area and volume of cones. In our last section on Thursday, we're going to talk about surface area and volume of spheres. Okay, but I'll go ahead and stop the recording right there.